Hello, my dear students. I am super excited to invite you all to another episode of our concept sharing session. And in this video module, I am going to talk to you about the basic concepts related to circles. So let's get started. The circle of life. What is meant by this circle? What is the circle all about? If you remember, when I started the first lecture on geometry, I indicated that it all starts with a plane. And in that plane, there are infinite number of points, right? Now, what is this circle? Let me explain. A circle, it is defined geometrically as the set of all the points that are lying in a plane, those points that are equidistant from a fixed point. This fixed point, we call it as the center. And this fixed distance, the equidistant, that word is used, right? This fixed distance from the center to any point that is lying on the circumference of the circle, that fixed distance, we call it as the radius. So let's consider the circle here. I am considering the center of the circle here. Generally, the center of the circle, it is represented using the letter O. I am considering a point P that is lying along the circumference of the circle. Let me now join this OP. Okay, so OP, it is a segment. So the distance from O to P, that distance, it will remain the same as long as I am considering all those points that are lying along the circumference of the circle. So this distance of the segment O to P, I am representing it using small letter r, and that distance, that's what we call it as the radius of the circle. So the moment we know r, it is the radius of the circle, then the perimeter of the circle, that is the circumference of the circle, we can calculate it using the formula 2 pi r. In the same way, the area of the circle, it can be calculated using the formula pi r square. And there is the diameter of the circle. Diameter of the circle, it is nothing but 2 times the radius of the circle. Okay. Now, I want you all to focus on something interesting here. From O to P, just see I am considering a straight segment here. Imagine I am now rotating this O to P in this manner. Okay. It's going one full round, as you can see, right? And finally, it has come back to the point P. I repeat, O to P you are considering. So I am just rotating this O to P, this segment in this way, as you can see. It's making one full round and now it has reached back the point P. And could you please tell me what is that angle that OP it has covered now? I can say it has covered full 360 degrees, right? So that's all about the circle of life. The full rotation, when you are considering, I can say 360 degrees. Okay, so make a note of that aspect. Now, let's talk about chord. A chord, it is a line segment that connects 2 points. Those 2 points are lying on the circumference of the circle. So let me consider the point P here. Let me consider another point here, Q. Now, please note chord, it is a line segment, which means it will be having a fixed length, a fixed measurement. Okay. So I'm just going to join this P and this Q. So this is that segment I am referring to. This line segment that has actually connected P and Q, those 2 points P and Q that are lying on the circumference of the circle, I call that PQ as the chord. Okay. Now please note, as this chord, it is moving towards the center of the circle, you can see that the length of the segment, it keeps increasing. Okay, for example, I am considering the center of the circle here as the point O. Okay, so you can see here, if I am considering another segment AB, okay, like you can see here where A and B, as I have marked here, B is here. Okay, just a second. I'm considering B is here and I'm considering A to be here. Okay, so AB is lying relatively closer towards the center of the circle, right? So the length of the segment AB, I can see that it is more than the length of the segment PQ. Okay, and as I am drifting away from the center of the circle, for example, let me consider ST. Okay, I have drifted more away from the center of the circle. I am considering ST here. You can see that the length of the segment ST, it is the shortest in this case, right? So that's what I was trying to explain here. As you are moving closer and closer towards the center of the circle, the length of that segment, that chord that we are considering, you can see that it keeps increasing. And thus, we will reach a particular point here. I can consider that that particular chord, it will be passing through the center of the circle. And that chord, it will be the longest chord associated with this circle. Okay. As I told you, as you are moving towards the center of the circle, the length of the chord, it keeps increasing. So finally, we can think about a chord, that is passing through the center of the circle. And that chord will be having the maximum length. It will be the longest chord. And that chord, we call it as the diameter of the circle. And that's what we saw earlier. From O to this point along the circumference, that distance, when I call it as R, same is applicable on the other side also, it is R. And that is how we said the diameter of the circle, it is equal to 2R units. All right. So make a note of these points here. So we have just talked about chord, and then what does this chord actually do? And we have also talked about the diameter of the circle. All right. Now, some properties associated with the chord, let us now consider. Okay. Equal chords, they are equidistant from the center. And the second point that you have to remember, it is the perpendicular drop from the center of the circle to a chord, it will bisect the chord. Two important results. I shall explain both. Let me consider a chord here, AB. Okay. Let me say that the measurement of AB, this segment AB, where A is one point on the circumference of the circle, B is another point which is lying on the circumference of the circle. That's why I'm calling AB as the chord. Okay, so let me say AB, it is equal to, let me say 10 units. Okay. Now I am considering another chord, let me say PQ. Okay, so this PQ, it is also 10 units in length. Okay, P, it is a point on the circumference. Q is also a point on the circumference of the circle. Let me say this PQ, it is also 10 units. Okay, let me consider that O, it is the center of the circle. So as per the first property that I have mentioned here, these two chords, they are having the same length, 10 units. We call these two chords AB and PQ as equal chords. and these equal chords, they will be equidistant from the center of the circle. So if I'm going to consider from O to this AB, perpendicular distance, from O to this PQ, the perpendicular distance I am considering, I can see that the distance from the center to chord AB, the distance from center to the chord PQ, they measure the same. The distance, it will be the same. So that's the first property that you have to consider. Okay. Now the next property that you have to deal with, the perpendicular dropped from the center of the circle to a chord, it will bisect the chord. So what does this mean? So here let me consider a chord, say AB, like what you see here. We can consider that this point A, it is lying along the circumference of the circle. B is also lying along the circumference of the circle. Let me consider that O, it is the center of the circle. Please note, the perpendicular that I am dropping from the center of the circle to this chord AB, okay, that perpendicular which I have dropped from the center of the circle to this chord AB, it is going to bisect the chord. What does that mean? It just means that this point where this perpendicular meets AB, let me take that point as P. Okay. So this OP, it will be making 90 degrees here with that of AB. Now this perpendicular that I am considering, OP that I am considering, it is going to bisect AB. What does that mean? It means that AP, it will be equal to BP. Got it? So they will be equal in length. They bisect the chord. This is an important result that you have to consider. Now, let's move on to the next concept. It's about tangents. A tangent, it is a line that just touches a curve at a single point without intersecting it. So let me consider a point P which is lying here. Now from this point P, consider I am going to draw a line like what you see. Okay, this line what I have drawn here that has started from the point P, I won't call it as the tangent. There's a different name for that, about which we will discuss. Because this point, this line, it has actually intersected the circle. It has cut the circle at two distinct points here. So this line, what you see here, I will not call it as the tangent. But consider from P, I am drawing one line like it is going. This line, you can see, just touches the circle here. Let me say this is the point Q where the line has just touched the circle. And this line, what you see here, I call it as the tangent. Okay. So tangent is a line. It just touches the curve at a single point. That single point, I call it as the point of tangency. That single point I am showing you here, that is the point Q. That line, it just touches the curve at a single point without intersecting it. Okay. Now for a circle, this tangent line, it intersects the circle at exactly one point, and that point we call it as the point of tangency. Okay. Now let me consider for this circle O, it is the center. Okay. Now, if I am going to consider OQ, okay, and OQ will be the radius of the circle, right? So this OQ, what you see here, it will be making an angle of 90 degree with PQ. Okay. So we can consider that in a circle, the tangent, it will be always perpendicular to the radius. So please make a note of this point. The tangent and the radius, they will always be perpendicular to each other as far as a circle it is concerned. Okay. Make a note of these details. Now, let's talk more about tangents, the properties of tangents. So I'm considering a circle here with center at O. I'm considering that line, that is the tangent. P, it is the point of tangency. I can call PO to be the radius, OP, PO to be the radius. And I'm extending that PO, I'm extending it to the point R. You can call that PR as the diameter of the circle. Okay. Now, the properties of the tangents. Let's consider the first property here. The tangent, as I mentioned earlier, it touches circle only at one point. And that point, the point P, I call it as the point of tangency. A tangent is a line that is never going to enter the circle's interior. Like I said, the tangent, it will not intersect the circle. It will not touch the circle at two distinct points, but tangent, it will touch the circle at only one point. And the tangent touches the circle's radius at the point of tangency at 90 degrees. So the radius and the tangent, like we saw, they make 90 degrees to each other. Got it? So these three properties, please keep in mind. Now let us talk about the two tangents theorem. I am not going to state that theorem and then explain it, but rather I shall present in front of you the results based on the two tangents theorem. Okay, so consider that we have a circle here. That circle has got the center O. I am considering there is a point C. From the point C, I am considering the two tangents to the circle. CA, I am considering it as the first tangent here. I call it as tangent number 1. CB, I am calling it as tangent number 2. Okay. Now, please note that the tangents drawn from the same point to the same circle, they will be equal in length. Look at CA and look at CB. I can see that CA, it will be equal to CB. The tangents drawn from the same point to the same circle, they will be equal in length. CA, it will be equal to CB. Now, the next result that you should be aware of, the two tangents will subtend equal angles at the center. So we considered O as the center, right? We can see angle COA. Look at this angle COA. Let me say it is alpha. Angle COB, it will also be equal to alpha. The two tangents CA and CB, they subtend equal angles at the center, as you can see. COA, it will be equal to COB. This is another result that you should be aware of. In the same way, the angle between the tangents, it will be bisected by the line joining the exterior point and the center. So you can see that CA is one tangent, CB, it is the other tangent. The CA and CB, they are showing an inclination, right? They are inclined to each other. There is an angle, what you can see here, right? So this angle, if you are observing, I am now considering joining C and O, as you can see. Okay, so just see, I'm joining this C and this O. So you can see this CO, it will be the angular bisector of angle ACB, which means ACO, if I say that is equal to theta, OCB, this also will be equal to theta. That's what point number 3 it says. The angle between the two tangents, it will be getting bisected by that CO that I have drawn. So that is another result which you have to keep in mind while you are solving problems. Okay. So let's continue with the concepts further. We will talk now something about secants. Now, what is the secant all about? A secant to a circle, it is a straight line that intersects the circle at exactly two distinct points. You remember tangent? I kept on repeating that it cuts the circle or it touches the circle only at one point, right? That's the point of tangency. But as far as a secant it is concerned, a secant to a circle, it is a straight line that intersects the circle at exactly two distinct points. And these points of intersection, they lie on the circle's circumference, and the secant line, it passes through the interior of the circle, connecting these 2 points. So I shall draw how that secant it looks like. Okay. So let me consider the point, say P here. Okay. Now I am going to consider this P. From this P, a line is passing in this manner. Okay. And you can consider that it extends further. It can even extend further. Okay. It's not just necessary that here, this thing, what I have drawn here, you should restrict it from P to A to B. I need to stop here. Like that, I don't want to say. I can extend it further. This is a line which is going. Okay. But you can say this point and this point, they are lying along the circumference of the circle. Okay. And I say that these 2 points, let me say it is A, let me say that it is B. What you see in front of you, it is the secant. A secant to the circle, it is a straight line that intersects the circle. You see, this line is actually cutting the circle at exactly two distinct points, the point A and the point B. And you can see that these 2 points, they are lying along the circumference of the circle. And you can see that the secant line, it is going through the interior of the circle that is connecting these 2 points. So I hope you got an idea what this secant it is all about. All right. Now let's talk more about secants. The key characteristics of a secant to a line. The 2 points of intersection. A secant line, it must cross the circle at 2 distinct locations. Like you saw earlier, the point A and the point B. Please note the secant, it extends beyond these 2 points. Unlike a chord, which is a line segment, a secant, it extends infinitely in both the directions. The secant, it can continue beyond the points A and B that I have shown you, because a secant is as such a line. Got it? But the chord, it is a line segment. That's one difference that you have to keep in mind. Now, the secant, it passes through the interior of the circle. The line that passes through the circle's interior, and hence I cannot consider a secant that is equal to or an equivalent to a tangent. Logic-wise, it is different. Okay. So these 3 points, make a note of the same. Now, some other interesting and important points pertaining to the circles, let us consider. I am considering a circle here. Let me say O, it is the center of the circle. Okay. Now, I am going to consider a secant here, which is starting from the point P. Okay. So I'm considering it cuts the circle at these 2 points, the point A and the point B. Okay. So make a note of this. It's point A, it's point B. Okay. These 2 points, they are lying along the circumference of the circle. And the secant, you can consider that it is from this point P I am considering. Okay. So it's a line, it is actually going in this manner. So there is no beginning, there is no end. But I'm considering it from this point P. You can see that it cuts the circle at A, it cuts the circle at B. In the same way, let me consider another secant here. Okay. That is again from the same point P. Let me consider it is cutting the circle at two distinct points here, C and D. So let me consider that this is the point D, and let me consider that this is the point C. Okay, so I hope you can see PB and PD I am considering. Okay, so the two secants I have represented. We have a result that you have to keep in mind. PA into PB, it will be equal to PC into PD. Okay. Using this results, you may be asked to solve some problems. PA into PB, it is equal to PC into PD. Okay, it's an important result. Now, we have got another result that is connecting the tangent and a secant. Okay, so let us consider a secant PAB, which is going that way, as you can see. Now I'm going to draw a tangent. Let me consider the tangent. It is, say, PT. Okay, so it's just touching the circle exactly at one point here. That is this point T. Okay. Now here also we have a result. PA into PB, it will be equal to PT into PT. I can say PA into PB, that is equal to PT square. So this is another concept which you have to keep in mind. PA into PB, it is equal to PT square. Very important result it is. Okay. Now, let's consider some more concepts here. I am considering the circle here. Let the center of the circle, let it be O. Okay. Now, I am considering a point here, A, that's lying along the circumference. Another point here, B, that is also lying along the circumference of the circle. Let me consider angle AOB. Okay, I'm considering angle AOB. In the same way, I am considering another point C, which is lying along the circumference of the circle. So I want you to consider here drawing a segment A to C. That C, it is lying along the circumference of the circle A to C, and then B to C. Okay. So if I say this inclination, this angle, if it is equal to theta, please be aware that this angle, it will be 2 theta. The condition is that A, B, C, they lie along the circumference of the circle. Okay. They lie along the circumference of the circle ABC. And also you have to consider that O, it is the center of the circle. So in that case, I can see that the angle that is subtended at the center of the circle, if I say it is equal to 2 theta, then the angle that is subtended over here, that ACB I am considering, that will be equal to theta. Okay, so that is another result which you have to keep in mind. Now, let me consider the circle with center O. I am now considering the diameter of the circle here. Okay, diameter means it's a chord that is passing through the center of the circle. So let me say AB, that is the diameter of the circle. Okay, so we can see that here there is a semicircle on the top, there is a semicircle on the bottom of that AB, like you can see, right? Now please note the angle in a semicircle. Consider that I am drawing an angle here. The angle in a semicircle, just observe here. The angle that is lying in a semicircle, it will always be, with whatever be the way in which you can see that it is aligned, you can say the angle in a semicircle, it will always be making 90 degree. Okay, so this angle will be 90 degree. This angle will be 90 degree, 90 degree, 90 degree. Okay, 90 degree. Like that, we can consider the result. It says the angle in a semicircle, it will always be at right angles, like you can see. Okay, so that is another result which you have to keep in mind. All right. Now, based on these points, if the problem comes, make sure that you are attempting them. Okay. Now, I'm going to talk about something called as an alternate segment theorem. I am presenting it in a very simple manner. You can Google and find out what exactly the alternate theorem it states, but I shall make it in a very simplified manner. Rather than using this alternate segment theorem and all these words, I will ask you to consider something called as a cyclic triangle. Okay. In other words, I can see that there is a triangle ABC. You see a circumcircle as I have mentioned earlier. Okay. Now let us consider a line that actually goes in this manner, DCE. Okay, as you can see, and I can consider that it's just touching the circle at the point C. I would rather even consider this as the tangent as well. Okay, so please note here, this angle BAC, it will be equal to angle BACC, which is something which I presented in green color, angle BAC. It will be equal to angle BCE. Okay. This alternate segment theorem, it tells the same thing, but they have used some other different words over there. But in a nutshell, this angle BCE and this angle BAC, they will be equal in measurement. In the same way, we can talk about angle ABC. It will be equal to angle ACD. Look at the pink color here. So this angle, let me call it as theta. Angle ACD, that also will be theta. Okay. And if you consider this value as phi and the green wala one as alpha, you can see that theta plus alpha plus phi, it should be equal to 180 degrees. You can see that is applicable with the DCE as well. Theta plus phi plus alpha, it is coming as 180 degrees. Okay, so basically, in a question, if you see a triangle with that line orientation DCE like what you see there, you can consider that this angle, it will be equal to the angle over here. In the same way, this angle, it will be equal to the angle over here. That's the same thing alternate segment theorem also tells, but with different words. So I have simplified it for you. Use this result for solving the problems. Okay. Now, let's talk about cyclic quadrilaterals. We have got some interesting results that you have to note. But before I talk about those results, let's talk about what is the cyclic quadrilateral all about. A cyclic quadrilateral, it means It's a quadrilateral, four sides are there, that is inscribed in a circle. So you consider that there is a circle here. You take 4 points which are lying along the circumference of the circle. Okay. So now you just join those 4 points. You see a quadrilateral, right? So this quadrilateral, I call it as the cyclic quadrilateral. It's a quadrilateral that is inscribed in a circle. Just now we saw a cyclic triangle, right? I just mentioned it, the cyclic triangle. Now from there, I'm slowly moving to the cyclic quadrilateral. Okay. So it means that there is a circle that passes through all the four vertices of this quadrilateral. These vertices, I call them as concyclic vertices. I'm throwing that particular word in front of you here because in the question, if you see there is a quadrilateral where the vertices are concyclic, you should be able to interpret that the quadrilateral given, it is a cyclic quadrilateral. Okay. So it looks like this, as you can see. So let me consider that the vertices are A, B, C, and D, as you can see. So this is how the cyclic quadrilateral, it looks like. Okay. Now, some properties associated with the cyclic quadrilateral, let me present. If I say that this angle, it is alpha, and let me say that the opposite angle, it is beta. Please be aware that alpha plus beta, that is equal to 180 degrees. Okay. In the same way, let me say that this angle is theta. Let me say that this angle here, it is phi. I can see that theta plus phi, that will also be equal to 180 degrees. So the result is that opposite angles associated with the cyclic quadrilateral, they are always supplementary to each other. Okay. Now, let me consider that here, the length of the segment AB, let it be equal to A. Okay. I shall mention it as A. Okay, I'll do one thing. I'll just, for convenience, I shall just erase these vertices A, B, C, D for the time being. Okay, capital A, B, C, D, let me erase it. Now just see. I'm considering the length of this segment is A. The length of the segment, let me say it is B. The length of the segment, it is C. The length of the segment, it is D. The sides I am saying. Okay. So, the semi-perimeter of the cyclic quadrilateral, it will be A plus B plus C plus D whole divided by 2. That's a semi-perimeter. Okay. So now, if you want to find the area of the cyclic quadrilateral, you can use the formula area. It will be equal to root of S minus A, multiply that with S minus B, multiply that with S minus C, multiply that with S minus D. Okay. So please note S, it is the semi-perimeter. Okay. A, B, C, D, they are the four sides. So semi-perimeter, it will be S minus A. Sorry, semi-perimeter will be A plus B plus C plus D divided by 2. So from this, we can just say that S minus A into S minus B into S minus C into S minus D square root, if you take, you can say that will give you the area of the cyclic quadrilateral. Okay. Now, for this cyclic quadrilateral, I can think of one diagonal here. Let me say that is equal to D1. The measurement, it is D1 units. Okay. And let me say there is another diagonal here. Its measurement, let me say that is equal to D2 units. Okay. So there is another result which you have to note here. This D1 into D2, that is the product of the length of the diagonals, D1 into D2, that will be equal to A into C plus B into D. This is another important result that you have to keep in mind. D1 into D2, that is the length of diagonal 1 multiplied with the length of the diagonal 2, D1 into D2, that will be equal to A into C plus B into D, where A, B, C, D, they are the respective lengths of the sides of the cyclic quadrilateral. Okay, so make a note of the same. Now, in the same way, we can go for another result here. Let me say that this is alpha. Let me say that this is beta. Okay, so please note the external angle at this point here. This external angle, I can call it as, say, theta. You can see that this external angle or the exterior angle, it is equal to the opposite interior angle. This theta, it will be equal to alpha. The reason is very simple. You can consider that this is a straight line, right? The one what I am drawing here, it's a straight line. So that is 180 degree. Okay. Now you see this alpha and beta, they are the opposite angles for the cyclic quadrilateral. Alpha plus beta, you can see that that is also supplementary. So beta plus theta, please observe alpha plus beta, that is equal to 180 degree. This beta plus theta, that is also equal to 180 degrees. So you can equate them alpha plus beta, it is equal to beta plus theta. The beta and beta will get cancelled off. I can see that the external angle, it is equal to opposite interior angle. Got it? So theta and alpha, they are equal. That is another result that will help you for solving many questions. All right. So these are some of the important, interesting points related to the cyclic quadrilateral. Now, let's conclude this video module by talking about tangential quadrilateral. As far as cyclic quadrilateral is concerned, you could see that there is a circle, and inside the circle, you saw a quadrilateral. It was a quadrilateral that was inscribed inside a circle. Think about something happening the other way around. That is, there is a quadrilateral, and inside that quadrilateral, you are actually inscribing a circle. So that type of a quadrilateral, wherein inside the quadrilateral, you are inscribing a circle, that type of a quadrilateral, we call it as the tangential quadrilateral. A tangential quadrilateral, it is a convex quadrilateral where all the four sides of that quadrilateral, they are tangent to a single circle, and that circle, it is drawn inside the quadrilateral. It touches the circle, it touches the quadrilateral exactly at one point, like what you see here. The circle, it will be lying full and full inside the quadrilateral only. Okay, so this type of the quadrilateral, we call it as the tangential quadrilateral. Here you can see that a circle, it is seen inscribed inside this given quadrilateral. Okay, so now we can see that the four sides of this quadrilateral, they are A, B, C, and D, like what you can see, right? So, as far as this tangential quadrilateral is concerned, we can see that A plus C, it will be equal to B plus D. Okay, so this is another interesting result that you can see here. This A plus this C, the total, what you get here, it will be equal to this B plus this D. Okay, so that result you can use for solving many problems. Now, I shall conclude this particular video module by giving you some important, interesting formulae related to cyclic quadrilateral. Using these formulae, you can find the length of the diagonal of or diagonals of the cyclic quadrilateral here, D1 and D2. How to calculate the length of the diagonals, you can use this. And as you saw, in a cyclic quadrilateral, you can see that the quadrilateral is inscribed inside the circle, right? So the radius of this cyclic quadrilateral, what we are considering, it can be calculated using the formula that I have presented here. And please note here, S that I have presented here, it is the semi-perimeter. Okay, A plus B plus C plus D by 2. For triangle, if you remember, we consider area of the triangle. It is equal to ABC divided by 4R, where R, it was the radius of that circumcircle, right? The circumradius we talked about. Something similar in line for a cyclic quadrilateral, this radius R, it is calculated using the formula that I have presented here. So you can by heart the same and then use it for solving problems. Okay. So with this, I am concluding this video module. In this video module, I have talked to you about all the important concepts that you should be aware of, that you should know for solving questions from the topic circles. Okay. So wish you all the best. Make sure that you are practicing well by solving more and more problems. Thanks for watching.